This is today's poser. You have 1 mole of loonies and stack them. How high is the stack? And how big is this number? How would we visualize it? Hello, I'm Mr. McBrien. This is SCH3U, molar mass. The Ontario curriculum states that students will describe the relationship between Avogadro's number, the mole concept, and the molar mass of any given substance. Today, we're going to review Avogadro's number, talking about particles from moles and moles from particles. Then we're going to talk about molar mass, finding the mass from the number of moles. And in class, we'll go through the worksheet. So, review from yesterday. How many particles are in a mole? That's right, 6.02 times 10 to the 23. What's the definition of Avogadro's number? And the answer is, Avogadro's number is the number of carbon atoms in 12 grams of pure carbon. So, how high is a mole of loonies? Well, if we go to Google, it'll tell us that a loonie is actually 1.75 millimeters thick. So it's fairly trivial to say the height is Avogadro's number times 1.75 millimeters. However, this number is a little bit tough to visualize, 1.05 times 10 to the 24 millimeters. We can convert it into kilometers, but that almost doesn't help. So we divide by 10 to the 6 to get 1.05 times 10 to the 18 kilometers. And this is still a number very difficult to visualize. But if we keep in mind that 1 billion is 10 to the 9, 10 to the 18 is 10 to the 9 times 10 to the 9, or a stack of 1 mole of loonies is 1 billion kilometers tall. And I don't know about you, but I still have trouble visualizing that. Well, let's try something else. The moon is 384,000 kilometers away. So the stack of loonies would actually go back and forth to the moon actually about 140 billion times. So we need something even bigger to measure. Well, distance at its largest is measured in light years, and a light year is about 1 times 10 to the 16 meters. So if we divide that through, we can find that our stack of loonies is in fact 100,000 light years tall. Light would take 100,000 years to travel from the bottom to the top of our stack of loonies. And this should give you an idea that a mole is a rather large number. Okay, let's talk about moles of particles for a second. Review what we talked about yesterday. A mole of particles is 6.02 times 10 to the 23 particles. A mole of carbon atoms, 6.02 times 10 to the 23 carbon atoms. A mole of water molecules, 6.02 times 10 to the 23 water molecules. And a mole of sodium chloride, well, that's 6.02 times 10 to the 23 sodium ions, and 6.02 times 10 to the 23 chloride ions. Pretty straightforward. So some examples of moles, pretty straightforward again. A mole of magnesium, 6.02 times 10 to the 23 atoms. A mole of gold, 6.02 times 10 to the 23 gold atoms. And similarly, we can go through compounds as well. And of course, our equation for number of entities, we can do more than talk about just 1 mole. We can calculate the number of entities by multiplying the number of moles, small n, by Na, to get the number of entities, large N. So if we have half a mole of aluminum, we can simply use the equation, multiply 0.5 times 6.02 times 10 to the 23, and get 3.01 times 10 to the 23 aluminum atoms. And vice versa, of course. So we can calculate the number of moles by having the number of particles and dividing by Avogadro's number. And we're simply rearranging our equation, of course. So 1.8 times 10 to the 23 divided by 6.02 times 10 to the 23 should give us, by my count, 3? Yes, 3 moles of sulfur atoms. So what about how much it weighs? Because counting particles isn't a typical activity for us. We can't weigh out moles on an analytical balance, for example. What we want to be able to do is convert information about number of moles to masses. So we do this using the molar mass. We simply consult our periodic table and work accordingly. So the molar mass of an element is the number of grams in 1 mole of that element. And it's equal to the atomic mass. So a mole of carbon atoms is 12 grams. A mole of magnesium atoms, 24.3 grams. And a mole of copper atoms, 63.5 grams, straight off of the periodic table. So, if we're asked to give the mass of a mole of bromine atoms to 0.1 grams or a mole of tin atoms, we can simply go consult the periodic table and pull those out. A mole of bromine atoms is 79.9 grams per mole. A mole of tin atoms, 118.7 grams per mole. Fairly straightforward. And in fact, if we want to talk about compounds, it's really not much more complex than that. The mass in grams of 1 mole is equal to the sum of the atomic masses. So if we have calcium chloride, we can find the mass to be 111.1 grams per mole. How do we do that? Very simple. We look at the formula, see that there's 1 mole of calcium in each mole of calcium chloride, multiply 1 times 40.1 grams per mole. But then there are 2 chlorine atoms in the formula. So we multiply the mass of chlorine, 35.5 grams per mole, times 2. Add these together, 71 plus 40.1 gives us 111.1. And we can do the same thing for dinitrogen tetroxide. So we can find that it's 92.0 grams per mole. How do we do this? Well, it's 2 times 14 grams per mole for the nitrogen and 4 times 16 grams per mole for the oxygen. Add these together and we get 92. Very straightforward. And our mass from the number of moles, really not terribly difficult. We can find the mass of a given number of moles. Mass equals the number of moles times the molar mass. So, for example, we can find the mass of 2 moles of propane, C3H8. We simply calculate the molar mass of propane, 3 times 12 grams per mole, plus 8 times 1 gram per mole for the hydrogen, gives us 44.0 grams per mole. But we have, remember, 2 moles, so we multiply 44.0 times 2 to give us 88 grams. So 2 moles of propane weighs 88 grams. And as long as we're comfortable with standard scientific notation, we can do the same thing for much smaller numbers of moles. In this case, we want to get the mass of 1.33 times 10 to the negative 3 moles of acetaminophen. It's the exact same process. We calculate the molar mass of acetaminophen, in this case 151 grams per mole, and then we simply multiply that times the number of moles, and we get 0.200 grams, or 200 milligrams, a standard dose of acetaminophen. So now in class we're going to work our way through the worksheet and proceed with the activity. So in today's class we reviewed Avogadro's number, talked about molar mass, learned how to calculate mass from number of moles and moles from the amount of mass. Hopefully by now you're becoming an expert with your calculator and scientific notation. Thank you for listening and have a great night.